Hi, thanks for joining us in this first video lecture for class. And as I'm sure we'll discuss in the class time, we want to use the sort of the class meeting time for more hands-on things like problem solving and stuff like that. And since that's going to be the focus, we'd like to, we need you to sort of study the lecture material content at home outside the classroom time. And then during the classroom, sometimes we would call this a flipped classroom strategy. We want to focus on solving problems, especially some of the difficult and challenging homework problems. So hopefully you'll appreciate that we will focus on team-based problem solving during the class time, and then we would have you sort of do the listening to the lecture content as well as taking notes. We will always have maybe I shouldn't say always, but we should usually have skeleton notes. You'll notice for the first chapter at least, we're going to use PowerPoint slides, but for the subsequent chapters, with some exceptions, we would have sort of skeleton handwritten notes type note system. And you'll see what I mean by that later. So I want you to go and grab the sort of well, for the first chapter, the PowerPoint notes from Canvas, and then be ready to take notes as we go over the content. And so I'm excited to go over this very first chapter with you, and good job on actually spending some time to taking a look at our lecture videos. And I should maybe give you a fair warning that we'll try to go through this pretty fast because this should be all review of the general chemistry. And in general, we'll try to have about 20 minutes of videos for each half of the content for that you should review or preview, I should say, for each class meeting time. So for the first class meeting time, I want you to go through this video and the next. Now, I should mention that there's a possibility I might go over the 20-minute just because I spent 3 minutes here sort of introducing our class and the whole thing. So forgive me for like going over the time, but usually we try to keep each video to 20 to 25 minutes and no longer. But anyway, so let's go through this Gen Chem material. Well, we're going to first start with discussing and reviewing atomic orbitals because that's the foundation of everything, right? Of course, in organic chemistry, we're going to be talking about carbon compounds and molecules, but we first have to understand what atoms look like, and orbitals especially are important because that's where the electrons are, right? And when you think about it, in chemistry, we don't really care about so much what happens to the nuclei or nucleus because they don't really do anything other than just keeping these positive charged protons, and that's it. All the changes happen with the electrons and where they reside. They go from one place to another, and that's how like one molecule becomes another molecule. And that's kind of what we are interested in organic chemistry. Especially on the introduction slide, I had sort of the cartoon depiction of DNA molecule. Everything that happens in biology is a result of organic chemical reactions. And so, but to build a foundation towards that, we need to understand what atomic orbitals are, or at least remember that, right? That's where the electrons like to hang out. The hydrogen 1s orbital is the simplest, and remember each orbital can occupy 2 electrons, and that's it, because anything more than that, one cop answer like why not more, it's because it would be violation of Pauli exclusion principle. Remember that says 2 electrons cannot have the exact same set of quantum numbers. If the 2 electrons have up to 2 electrons can occupy the same orbital because the quantum numbers for the orbital would be the same, but the 2 electrons can have the opposite spin state or spin directions, and that would be allowable by Pauli exclusion principle. But if you had a third electron, 2 of the 3 would have to have the same spin state. And of course, the next up orbital would be 2s, and that would be right here, and then that's higher energy than 1s because it's further away from nucleus, and the electrons, being negatively charged, want to be close to the positively charged nucleus. Where's the node? It would be right here in between the 2 orbitals. P orbitals would be next, and they look like that, right? And remember, this is 1 orbital. These 2 colors are the 2 phases. S orbitals didn't have that feature, but the P and above, they all have like a different phases within a orbital. And because these shapes can point in like 3 different directions in a 3D world, there's 3 degenerate, meaning identical 2s orbitals, and they do also have a node in the middle at the nucleus. And you guys probably remember filling out these electron configuration diagrams, right? There's these, as you go from hydrogen to, like, say, neon, which is hidden by my big face, like you have to follow these principles. Hopefully you remember from Gen Chem, and if you don't remember what these are, I would encourage you to go look them up. I might review with you Hunt's rule. That's when you get to nitrogen, you might, when you get to boron or carbon, I should say, you might think this second electron in the 2p orbital would show up here to pair up. But electrons behave kind of like us on a public bus, right? All the seats are usually love seat configurations where 2 people can sit on a seat. Unless you're a weirdo, you spread out first, right? Like you go find another seat, and then once all the love seats are occupied by at least 1 person, then you're gonna have to stop pairing up. That's how electrons like to roll as well. And remember that electrons, they have these dual nature. They can act like a particle, but they really kind of at the heart are behaving like a wave, right? And so for that reason, there can be such thing as an interference of waves. If the 2 waves that collide with each other or interact with each other have the exact same phase, then they can have constructive interference. That means that the amplitude in the middle increases, whereas if the 2 waves that interact have the opposite phases, then they'll cancel each other. That's called destructive interference, creating often a node even in the middle, right? And why is that relevant? Why do we care? Well, this amplitude, like how big the wave is just sort of portraying like how likely electrons would hang out at that particular location. That's what the electron wave function tells you. Big wave means there's a really good chance there's electrons here. Tiny wave, or even worse, a node, meaning there's a 0 amplitude here. That means there's a 0 chance of electrons being found at that location. If there's a constructive interference, that results in a bond, and where is the favorite spot for electrons to hang out? That's the highest amplitude locations where there's constructive interference. And that's what molecular orbital diagram shows you, right? Which molecular orbital, remember, by definition extends out to the whole molecule instead of localized to a single atom. And you can have destructive or constructive interference molecular orbital. When you mix 2 atomic orbitals, you get 2 molecular orbitals. This diagram doesn't mean you got 4 at the same time. You mix these 2 to get 2 molecular orbitals, right? That's how it is for hydrogen. And remember this principle that you get the same number of molecular orbitals as the number of atomic orbitals you mix to make the molecule. That's called linear combination of atomic orbitals. Now, why is the anti-bonding molecular orbital high in energy? Well, it's because there's a node. Well, why does that make it high energy? Well, if you think about it, a covalent bond, it's kind of weird how two atoms that have the same charge, positively charged nuclei, they want to bond together at all because those two nuclei should repel each other. They both have positive charges, right? But they actually are happy to bond, and that's a good thing because that's the only reason why we exist, because we're made of molecules, if you didn't know. um, they like to bond because they share electrons, and electrons if they happen to have high amplitude of wave function in the middle, they would hang out in the middle, and so the two positively charged things who would normally repel each other can bond together. It's kind of like if you've ever been in a trio, three friend group where two of you hate each other. Maybe two of you are like guys, and like maybe you two like hate each other for some reason, but you stay in this three people friend group because the third person is this girl that both the two guys are interested, or some complicated situation like that. If you've been in that situation, you can understand the only reason why the two of you hang out is because of that one girl. It's kind of similar situation here. Hopefully that analogy is helpful. And when um, and right, and that's why the bonding molecular orbital is stabilizing for the whole molecule. But anti-bonding molecular orbital, it's not, because electrons don't hang out in the middle, right? So the nuclei would just want to repel each other. And that's why, by the way, helium-2 molecule doesn't exist, because of the 4 electrons that you would have to account for in a helium-2 molecule. You would have to put 2 anti-bonding molecular orbital electrons, or in the anti-bonding molecular orbital, excuse me, which has this really high energy because it only contributes to repulsion between the two nuclei, which is not good, right? So here's an interesting sort of general question. If a molecule has all of its molecular orbitals occupied, there's a typo there, will it be stable or unstable? The answer, of course, is unstable, because necessarily you would have to fill the antibonding molecular orbitals as well. And you probably remember talking about hybridization of atomic orbitals, because otherwise you can never explain things like methane, which I hope you believe in methane, it exists, right? Which is kind of weird, because if you look at the atomic electron configuration of carbon, there's only 2 orbitals that seem like capable of forming bonds. Because remember, covalent bond means you share 2 electrons total, which usually means one atom brings 1 electron to the table, the other electron brings the other electron to the table, and the 2 share those 2 electrons, right? So maybe you could have CH bond here and a CH bond here with another hydrogen, and that is it, CH2, with a weird, 90-degree orthogonal geometry. And yeah, methane looks like this. So there has to be something else going on here with 4 equal CH bonds, right? And so does that come from just exciting one of the electrons in 2s to 2p? Because then now there's 4 orbitals with 1 electron each. So it seems like it could make 4 bonds, but these 3 are different than this one. So geometrically wise, like this is not going to look like methane, because there's hydrogen here, here and there, and I don't even know where to put the 4th one, right? Because 4th one would have to be the spherical 2s. So that still doesn't explain the methane geometry. So something else has to happen, and that is hybridization, where these 4 orbitals come together and hybridize to make a new type of orbital, sp3 orbital. It's called sp3 because it's made of, each one is made of like parts of 3 parts p and 1 part s. right? So that's sp3 orbitals, and there's 3 of them. Each of these is sp3 orbital. And that, what would that look like? It's 75% P and 25% S, so it should look like this, because hopefully it makes sense, because S has that spherical shape, so one side would have a destructive interference, because S only has one phase, and P has 2 phases, so the other side would necessarily have constructive interference with the S and gets bigger. The other side gets smaller because of destructive interference. And so now you could have 4 equal sp3 orbitals. And yeah, and so remember that each one has this type of shape. Okay. And what about ethylene? Well, ethylene would have to bond with, well, the carbon has to bond with 3 things. 3 atoms. That means you need 3 hybridized orbitals instead of 4 like methane. And so you would hybridize these 3 lowest energy orbitals, and you leave one of the p's untouched. So you would end up with a situation like this, where you can make 3 bonds with these 3 sp2 orbitals. It's called sp2 because you only mix 2 of p's and 1 of s. And then you have 1 p that's intact, and so you would have this shape where you got 3 sp2 orbitals and 1 p orbital that's intact. And so one of each of those sp2s can form a bond with a hydrogen, another hydrogen, and a carbon. And this would be a sigma bond. Sigma bond is when you have this head-to-head overlap of like a really tight secure overlap of orbitals is when you have a sigma bond, right? So each carbon has 1, 2, 3 sigma bonds, 1, 2, 3 sigma bonds, with 1 p orbital left over. And those can have this side-to-side overlap, which is not as strong as this head-to-head overlap, and hence this is going to explain a lot of the chemistry that we'll learn in this semester. Pi bond is always weaker than sigma bond because pi bond is this like weak side-to-side overlap, whereas sigma bond is like this really tight head-to-head overlap, and which is also depicted in the molecular orbital depiction of the molecule. Right, the pi bonding molecular orbital goes over the whole molecule like this. That's where the electron likes to hang out. We don't have to worry about the anti-bonding molecular orbital because you don't put any electrons in there for ethylene anyway. If you consider acetylene or ethine, right, now the carbon only has to bond to 2 atoms, so you only need 2 hybridized orbitals, and that's why you form 2 sp orbitals. The linear combination of atomic orbitals still apply. If you mix 2 orbitals, you get 2 orbitals. Right? If you hybridize 2 atomic orbitals, you get 2 hybridized atomic orbitals, 2 sp orbitals, and you leave behind 2 of the 2p orbitals behind. So the shape would look like this, necessarily 180 degrees bond angle. So you got sigma bond here, sigma bond here. These are the 2 sp orbitals. Here's sp orbital overlapping with 1s orbital of hydrogen. Here's sp of one carbon, sp of the other carbon, forming the CH sigma bond, CC, sigma bond in acetylene or ethine. And then you got 2 of these p orbitals on each carbon, so you could form 2 pi bonds. That's acetylene. Now, just to practice to make sure that you've got hybridization and all of that mastered, let's think about this. Maybe you could pause the video here for a sec, and then maybe I'll show you the first one. Like this carbon, it's attached to 4 things, so it has to be sp3 hybridized and so forth. Can you assign the hybridization to each of these carbons? So pause the video, see if you can do it. All right, so here's a carbon with 3 things attached to it, it must be sp2. Same thing with this carbon, it's sp2, sp2. That's sp3 because 4 things. This is attached to 2 atoms, so it has to be sp. Same with this sp, sp3, sp3. Hopefully you're getting the hang of it. This is attached to 4 things, 4 atoms, so it's sp3. This is attached to 3 atoms only, so it's sp2. Now this is sp2, 3 atoms. This kind of looks like that because it's also got double bonds, but if you look at it carefully, it's only attached to 2 other atoms, so it's sp, sp, sp2. So you don't have to have a triple bond to be sp hybridized. You just have to have 2 pi bonds on that carbon. So this is sp, whereas this is sp2. Hopefully that makes sense. And all that hybridization is important because that explains the geometry or the shape of the molecule, right? Hopefully you remember a diagram like this from Gen Chem. You might not have used the exact same terminology, but some Gen Chem classes we would say that you look at the steric number. That's just another way of saying how many things does a central atom have, counting lone pairs as well as attached atoms, right? So tetrahedral arrangement of electrons can have tetrahedral molecular shape or trigonal pyramidal with the 4th thing being a lone pair, or bent if there's 2 lone pairs, 2 pairs of lone pair electrons, and so forth, or linear, trigonal planar from sp2. Hopefully all that rings a bell, and see if you can fill in the blanks here by pausing the video real quick. Right, the trigonal pyramidal and bent, right, and the electron group geometry might be different than the actual molecular geometry because of the lone pairs of electrons that are non-bonding, and that all of that molecular geometry explains the polarity of the molecule, and that is an important thing to think about in chemistry in general, but especially in organic chemistry. Here's an interesting alkane molecule that's halogenated. It has halogens on this hydrocarbon molecule. It's called halomen. It's a natural product, naturally produced non-primary metabolite molecules that are produced by this marine algae that we found some years ago. We as in like the scientific community, I didn't. Well, I've studied marine red algae from marine natural products, but I didn't find this one. This one, because of its particular polarity, it's able to go through the cell membrane and get into the cell and kill some human cells. And for that reason, it's being studied as a potential anti-cancer agent. And all of that comes directly from the polarity of the molecule, which is predicted by the molecular geometry. So here's one more practice for you. Analyze the steric number, hybridization, and electron group geometry, and so forth for this, which, by the way, has that same structure. That we'll talk about that line structure and what that means. This is sp2 hybridized nitrogen. Sorry, I meant to say, I should have said predict the steric number and so forth for the nitrogen. By the way, this is also sp2, but that's sp3. Again, it's really important to figure out the molecular geometry so that you can figure out the polarity, right? Because the net dipole moment, if you recall, depends on the actual molecule's shape. Like if the water molecule was linear instead of bent, there would not be this net dipole moment and it would not be polar. If it's not polar, well, water would not exist as it exists, and it doesn't do what it does. So we would none of us would exist. Some of the things we might consider in our class this year would be some introductory medicinal chemistry type of concepts, like why does this penicillin G structure have the bioactivity to kill bacterial cells or stop them from growing. Well, yeah, part of it has to do with this four-membered strained ring, but the other reason is because of the polarity of this molecule.